All right, let's talk about the hidden language the universe uses to keep its energy books balanced. This is a huge concept in thermodynamics, and honestly, it's at work all around you, in your car, the power plant that lights your home, pretty much everywhere.
But let's start with a question you've probably heard before. Does the path you take matter more than your destination? You know, in life, that's a pretty deep philosophical question. But in thermodynamics, the answer is a very clear, it depends. And figuring out what it depends on, well, that's everything.
So let's dive right into this thermodynamic puzzle. Now we're going to use a super classic example to do it. A simple piston in a cylinder. Okay, so picture this. You've got some gas trapped in a cylinder. It's just sitting there in a very specific, well-defined condition. It has a certain pressure, it takes up a certain amount of space, its volume. Let's call this our starting line, state 1. Now we let that gas expand. As it does, it shoves the piston outwards, and by doing that, it's doing work. This continues until it gets to our finish line, a new state with a lower pressure and a bigger volume. We'll call that state 2. Simple, right? So, how much work did the gas actually do? Well, here's a cool trick. If you plot this whole process on a graph of pressure versus volume, the work it did is just the area underneath the line that connects state 1 to state 2. For instance, we could make the gas expand in a very specific way, following what we'll call path A. The area under that path gives us the amount of work we got out. Easy enough? But what if we shake things up? What if we start at the exact same state 1 and end at the exact same state 2, but this time we force the gas to expand along a totally different route? Let's call it path B. And this is where our puzzle comes in, because if you look at the graph, the area under path B is clearly different than the area under path A. That means the work done is different. We started in the same place, we ended in the same place, but we got two completely different answers for the work.
So what's going on here? How is that even possible? How can the work, a type of energy, depend on the journey and not just the destination? This little paradox is actually a huge clue that reveals something fundamental about how the universe does its accounting. To really get this, we need to make sure we're using the right words. We have to nail down the difference between properties of a system and the processes it goes through.
First up, we have properties, or what scientists often call state functions. These are things that only depend on the state the system is in right now. It doesn't care how it got there. Think of it like this. If you climb a mountain, your final altitude, say 10,000 feet, is your altitude. It doesn't matter if you took the short, steep trail or the long, winding one. 10,000 feet is 10,000 feet. It's a property of your location, not your journey.
So back to our gas in the cylinder. Its pressure, temperature, and volume, those are all properties. Their values at state 2 are what they are, and it makes no difference if we got there by path A or path B. The same is true for its internal energy, which is basically all the tiny little microscopic energies whizzing around inside.
But then you have the other side of the coin, path functions. These guys are all about the journey. Back on that mountain, the total distance you walk to get to 10,000 feet, that completely depends on whether you took the short trail or the long one. Distance walked is a path function.
And as we just saw with our piston, work is the classic path function. So is heat. Now, this is a really important point. These are not things a system has. Your gas doesn't contain work. Work and heat are energy in transit. They only happen during a process, as energy is being transferred.
So you can imagine, with a distinction this important, scientists and engineers needed a clear mathematical way to tell these two things apart in their equations. A little piece of shorthand to say this only cares about the destination versus this one's all about the journey.
And the way they did it is actually kind of brilliant, using the language of calculus. For properties, the state functions, they use what's called an exact differential, and they write it with a normal d. But for path functions, they use an inexact differential written with the squiggly Greek letter delta, delta.
Now, this notation might seem small, but it is so powerful. When you see dV, that means a tiny change in the volume. The volume is a property the system has. But when you see delta W, it means a tiny amount of work done. You can't say a change in work because the system never had work to begin with. It's such a tiny, subtle distinction, but it means absolutely everything. Okay, so now that we have this new language, let's see how it all comes together in one of the most important rules in the entire universe. The first law of thermodynamics. This is where all our puzzle pieces just click right into place. At its core, the first law is just a fancy way of saying energy is conserved. You can't make it, you can't destroy it, you can only move it around or change its form, and you do that with heat and work.
And here it is, the whole thing, written in our new language of differentials. And because we know what those d's and deltas mean, we can finally appreciate just how elegant this little equation is.
It's telling us that a tiny change in a property this system has, its internal energy, du, is perfectly balanced by the tiny amounts of energy that cross its boundary during a process, the heat you add, delta Q, minus the work it does, delta W. A state function is defined by the balance of two path functions. It's just beautiful.
Now, you might be thinking, okay, cool theory, but why should I care? Well, this whole idea, this distinction between path and state, is literally the secret weapon engineers use to design just about every machine that powers our world. I mean, just think about a car engine for a second. To make it more powerful or more efficient, engineers don't just care about the start state, fuel and air, and the end state, exhaust. No way. They are obsessed with designing the perfect path for the combustion cycle to follow. They want to shape that curve on the pressure-volume diagram to make the area underneath it as big as possible, to squeeze every single drop of work out of that fuel.
And that leaves us with a final little thought to chew on. We know that in the real world, every path has friction and losses and all sorts of messiness. So what is that perfect, idealized path that engineers are always trying to get closer to, but can never, ever quite reach? Well, that perfect process has a name. It's called a reversible process. But that is a story for another time. Thanks for joining me.